Hello and welcome to today's webinar on electrical safety for August 17, 2016. The material in this presentation is provided by Liberty Mutual and prepared for POAH communities where safety comes first. While electricity is essential for our day-to-day lives, both at work and at home, electricity can also pose a serious hazard. Serious injuries and fatalities can occur even with the voltages of 110 volts, the most common household appliances run on. The odds on dying from an electrical accident are higher than almost any other accident, 1 in 7. OSHA defines high voltage as 600 volts or more, but 75% of all electrical accidents occur at voltages under 600 volts. Managers and leaders need to realize that costs of electrical accidents are twice as high than any other accident. When electrical shock enters your body, it may produce different types of injuries. One is electrocution, which can result in internal and external injury to body parts or the entire body, often resulting in death. After receiving a jolt of electricity, all or part of the body may be temporarily paralyzed, and this may cause a loss of grip or stability. A person may also involuntarily move as a result of receiving electrical shock, resulting in a fall. Internal or external burns also may result from contact with electricity. Overhead and buried power lines are especially hazardous because they carry extremely high voltage. Fatal electrocution is the main risk, but burns and falls from elevations are also hazards when working with electricity. Using tools and equipment that can contact power lines doubles the risk. Normal use of electrical equipment can cause wear and tear that results in insulation breaks, short circuits, and exposed wires. There is no ground fault protection. This can cause a ground fault that sends current through the worker's entire body, resulting in electrical burns, explosions, fire, or even death. If the power supply to the electrical equipment is not grounded or the path has been broken, fault current may travel through a worker's body, causing electrical burns or death. Even when the power system is properly grounded, electrical equipment can instantly change from safe to hazardous because of extreme conditions and rough treatment. If electrical equipment is used in ways for which it is not designed, you can no longer depend on safety features built in by the manufacturer. This may damage your equipment and cause yourself injuries. The normal wear and tear on extension and flexible cords can loosen or expose wires, creating hazardous conditions. Cords that are not 3-wire type, not designed for hard usage, or that have been modified increase your risk of contacting electrical current. This is why it's so important to make sure the equipment that you're using is in proper shape and the procedure that you're using those equipment is done correctly. Electrical power lines are an obvious exposure when they are overhead in the street, but unfortunately they're not so obvious when they are underground or in walls or floors. Extension cords are very common in the workplace as well as at home. Most machinery is powered by electricity. Electronic equipment is clearly powered by electricity but also has hidden high voltage exposures in capacitors. Switch boxes, circuit breaker boxes, termination boxes, and electrical sockets are other clear exposures for electronic hazards. Let's get a little more scientific here. The following is an example of a simple circuit. We have a power source, which is a battery or generator, wires or conductors with a light. For electricity to flow, we need to complete the circuit. A circuit is any system of interconnected wires, metal parts, which form a closed, organized path through which electricity can flow, like water. The loop from the battery through the light and back to the battery is a circuit. Let's go over some electricity terms. 4 important interrelated aspects of electricity circuits are voltage, current, resistance, and power, sometimes called wattage. The flow of electricity in a circuit is sometimes compared to the flow of water through a pipe. Voltage is the pressure that pushes electricity through that circuit, like pressure that pushes water through a pipe. This is measured in volts. Voltage is generated by a battery or electrical generator, which is equivalent to pumping water through a pipe, as I just said. Current is the amount of, or quantity of electricity flowing in the circuit measured in amps. Resistance is the opposition of current flow in a circuit measured in ohms. And power or wattage is the total power load of a circuit and is measured in watts. Grounding is a safety measure that is added to a circuit to protect people and equipment from accidental contact with electric current. Electricity flowing through a normal circuit requires at least two wires. One is the hot wire, either red or black, which carries the current. The other is the neutral, normal white wire, which is connected back to the power source. Could be the circuit breaker panel, completing the circuit. Usually the neutral is connected to a metal water pipe or a rod buried in the ground near the panel board, and it is said to be grounded. This is called circuit or system grounding and is necessary for current to flow. The object of safe and profitable use of electricity is to keep it all flowing within the planned path or circuit, and not let it leak out into adjacent conductive materials. If a leak occurs, power is wasted, and an accident or fire could potentially occur. Working with ungrounded hand tools can be very dangerous. Hand tools are designed to do their work, but they also can vibrate and heat up. This can eventually wear out the insulation or cause wires to break. Carry tools by their wires can also wear out the insulation. The tool will still operate, but the tool housing can become electrically charged or hot, which can cause a serious shock or fatality. With proper grounding, the electrical current could flow through the grounding wire back to ground. If the ground prong is missing or removed and the tool's housing is hot, then you must not use this equipment. Pictured here is another system, which is called protective or equipment grounding. This system is vital for protection of anyone in contact with an electrical device. It consists of an extra wire, normally colored green, extending the length of the circuit and also attached to a metal water pipe or rod buried in the ground. Unlike the system ground, the equipment ground normally does not carry current. It provides a low resistance path to ground whenever the current leaks. This ground can allow another current to flow to the ground to cause an overload and blow a fuse or trip a circuit breaker, which shuts off the current flow and calls attention to the problem. Double insulation, although is the most common method of protecting against electrical shock, is the use of a 3-wire cord and plug. Double insulation provides reliable protection under certain conditions. This method is most often used in portable power tools where the entire tool is completely encased in a non-conductive housing, usually reinforced plastic. Larger capacity tools and those using voltages higher than 110 volts require additional strength and protection. This is provided by an internal layer of insulation, isolating the electrical components from the outer case. This insulation, which is in addition to the normal insulation provided by the cord and plug, eliminates the need for a third grounding conductor. Let's get a little more scientific here. Ohm's law states that the amount of current that flows in a circuit is directly proportional to the voltage, but inversely proportional to the resistance. Therefore, with a constant resistance and an increased voltage, more current will flow. With a constant voltage and increased resistance, less current will flow. Assuming that a circuit has 110 ohms of resistance and 220 volts, what is the ampage? The answer is 2 amps. The numbers in the previous slide take on greater significance when we see how the body reacts to the flow of varying amounts of current. At 50 milliamps, the body's muscles contract and do not let go. By applying Ohm's law, A 50 milliamp exposure and 100,000 ohm resistance corresponds to 50 volts. This explains why we saw in the previous slides, which is OSHA's 50 volt limit. Using this information and the previous information on skin resistivity, it can be concluded that as soon as the skin becomes moist, the human body is in grave danger when it comes to electrical circuits. An important factor for electrocutions is the path of current flowing through the body. Current that enters in the hand and exits at the elbow is not as dangerous as current that passes through the heart or the lungs and any other major organs in the body. Another consideration is the amount of time you're in contact. A low current contact for a few seconds can be just as dangerous as a high current contact for a few hundredths of a second. Other important factors enter into the possibility of electrocution. Larger areas of exposed skin allow more current to enter the body. A person in good health has a better chance for recovery than a person in bad health. The promptness and quality of first aid also affects the chance of recovery in a victim of electrical shock. When investigating the unsafe condition that caused the accident, generally it exists because of an earlier unsafe act committed by someone, possibly not by the victim. The key to preventing electrical accidents is to identify the unsafe practices and conditions which cause electrical accidents and then work out a program and a procedure to prevent them from occurring. Well, let's think about the typical unsafe practices that you may observe, and then develop a basic electrical safety program that should be part of any of your overall safety effort. For instance, the picture previously, when working in a wet area, if you have dry skin, it's about 0.0002 amps. But when you're perspiring or moist skin, it's 0.11 amps. And in water specifically, it's 0.73 amps. At 110 volts, this could mean that the following current flow in the body would be the highest in water. The higher the amperage, the higher risk of serious injury or death. The human body can have high resistance, but it can vary, as this illustrates, depending on sweat and water conditions. When you're at a higher risk in a certain area, where you're wearing jewelry, where you're working without PPE, when there's no GFCIs, no ground connection, ungrounded tools, you're going to have a higher risk of taking on too much electricity and with possible severe injury and death. Regular safety inspections are so important to identify hazards and unsafe acts. Make sure you're doing consistent and subsequent follow-up surveys to determine if these situations have been corrected. If a procedure has not been corrected, you may be continuously putting yourself at risk. Any new equipment that you bring onto site must meet code and safety requirements before it's allowed to operate. You also must make sure that everyone on your team is capable and understanding of how to operate the equipment safely. A risk assessment could be conducted to identify any potential hazards that come with that equipment, and controls should be implemented prior to any operation. Special hazard jobs should be planned so that adequate safety precautions can be taken. Determine and enforce safety procedures for jobs such as tank cleaning or working in wet areas. Let's review a little bit of the lockout-tagout procedure. Step 1 is prepare for shutdown. Notify affected employees or activities, identify shutdown procedures, identify energy sources, identify the energy isolation devices, and determine quantity and type of lockout-tagout devices required. Step 2 is the actual shutdown. Shut equipment down by its normal stop-start method. Then step 3, isolate the energy sources. Using energy isolating devices appropriate for the energy source, such as manually operated circuit breakers or electrical disconnects for electrical energy, values for pneumatic energy, or blocking or bars for mechanical energy. All devices must be equipped with a place to attach a hasp or a lock or have a built-in locking mechanism. Step 4, apply locks and tags. Locks are attached so that the device cannot be operated until locks are removed. Devices must be in the off position. Tags indicate that the device and equipment may not be operated. Some equipment may not allow for locking. In this case, it is extremely important that tags and signage is very obvious and bold so that anyone observing or working in the area knows that work is being conducted. Locks, tags, signs, and seals must be securely attached. The name of the authorized employee must also be included. Step 5, control residual energy. Release, restrain, or dissipate energy. Prevent the reaccumulation of energy. Isolate the space, blind the lines, disconnect and misalign the lines, double block the valves, and bleed the residual materials. Step 6, verify energy control methods. Assure that switches, valves, and other mechanisms cannot be turned on. Activate equipment control switches and levers and depressing start buttons to assure the power is isolated. Return switches, levers, and buttons to the off position. Use a meter to assure that electrical energy is not present. After developing specific work methods and use of personal protective equipment, explain the regulations to anybody working in the area and enforce the use of such equipment. The equipment needs to be the proper type for each job, and all the employees should receive training concerning how to use and maintain it. When an accident occurs, no matter how slight it might be, make a thorough accident investigation to determine what unsafe conditions and methods existed and what corrective action needs to be taken. Remember, the majority of electrical work we will hire a licensed electrician to take on. If you feel unsafe doing the work, you should always explore other options. Finally, make sure to establish a written emergency response procedure to handle electrical injuries and medical emergencies. Train employees on your site on these methods and conduct drills on a periodic basis. This may seem like a large amount of information that has been covered in this session, but it will be time well spent if you apply what you have learned, especially when you consider the following. Only 1 of every 300 accidents is lost time. Only 1 of 30,000 accidents results in death. However, 1 of every 7 electrical accidents is fatal. Remember this when working with electricity and taking on safety procedures. Thank you for listening and have a great day.